Please pause the video and try the problem. Now let's discuss the problem. Here is a summary of the solution for part A of the problem. And let's go through this solution step by step. The problem mentions concepts of mass, friction, which is a force. Here's another force. Then in part B, again, the problem refers to force and acceleration. All of those concepts fit into a Newton's second law problem-solving framework. So that's the framework we'll apply for this problem. Now let's make a note of what the question for part A is asking us for. The problem asks for the minimum force necessary to make the block start moving up the incline. Now, the problem already has told us the direction of that force. So I'm going to interpret this question as just asking us for the magnitude of this force. When possible, it's good to represent the question with a symbol. So I'm going to use this symbol, F sub applied, written without an arrow on top, to stand for the magnitude of this applied force. Now, although the question asks about the minimum force, we can interpret that question as asking us for the borderline force, the force at which the block is on the borderline between moving up the incline and not moving up the incline. The question is really asking us for the borderline applied force at which the object is on the borderline between sliding up the incline and not sliding. The problem refers to the minimum force necessary to make the block start moving up the incline. That means that if the force is greater than this minimum, the block will slide up the incline. And if the applied force is less than that minimum, the block will not slide. Since our goal is to determine the magnitude of this borderline applied force, in order to solve the problem for part A, we are going to assume that the magnitude of the applied force is equal to the borderline value. Now we know that if the applied force is greater than the borderline, the block will slide up the incline. And we know that if the applied force is less than the borderline, the block will not slide. But what do we expect to happen if the force is equal to the borderline value? Well, this may seem strange, but when the applied force is equal to the borderline value, you can assume either that the block will slide or that the block will not slide, whichever is convenient for solving this part of the problem. So is it more convenient to assume that the block will slide at the borderline or that it won't slide? Well, to answer that question, it helps to understand what type of question we're working on for part A. Here again is the Newton's second law handout that we discussed in the first video in this series. Let's turn now to page 2 of this handout. Page 2 of the handout summarizes how to solve different types of problems involving friction. Now, this first box involves objects that we know are sliding. These are the types of problems that we've been solving in the previous videos in this series. But for part A of this problem, we're going to move down to the second box. This second box is the method that we should use for maximum or minimum problems involving whether an object will slide. And that's what we're working on now for part A of this problem in this video. We're working on a minimum problem involving whether the object will slide. For this type of problem, we will use a Newton's second law framework. We will assume that the object is on the borderline between sliding and not sliding. And here's the useful part. It turns out that for this type of problem, the useful assumption is to assume that at the borderline value, the object does not slide. For maximum or minimum problems involving whether an object will slide, it turns out that the useful assumption is to assume that at the borderline value, the object does not slide. So here I've written down that assumption. We're going to be assuming for part A of this problem that at the borderline applied force, the block does not slide. Now this might seem like a strange assumption for part A because part A refers to the force that will make the block start moving. Nevertheless, it turns out that at the borderline value for the applied force, it is a valid problem-solving technique to assume that the block does not slide. Notice that I've written down the assumptions that I'm going to use to solve part A. Now we're assuming for part A that the block does not slide. For this problem, if the block is not sliding, that means that the block is motionless. So I'll write down that for part A, the velocity of the block is 0. The problem mentions units of kilograms, which are SI units. Now let's work on the free body diagram for the problem. We begin by identifying the object's weight. Now we ask, what is touching the block? The block is being touched by the inclined plane. An inclined plane is treated as a surface, which will exert both a normal force and a frictional force on the block. For part A of this problem, should we apply static friction or kinetic friction? Well, remember that for part A, we're assuming that the block does not slide. When an object does not slide, the correct type of friction to apply is static friction. So for part A, the block will experience static friction. Furthermore, since we're assuming that the object is right on the borderline of sliding, we will be applying the maximum static friction. Is there anything else that is touching the block? Well, yes, we know that someone else is touching the block in order to exert this pushing force on the block. That's the force that part A is asking us to determine. I'm going to refer to this force as an applied force, and I'll use the symbol capital F sub applied to stand for that force. Besides the inclined plane and this someone, there's nothing else that is touching the block. So there are no other forces to include in the free body diagram. We can use these two rules to determine the directions for the normal force and the weight force. The normal force exerted by the incline on the block will point perpendicular to and away from the surface of the incline. Perpendicular to and away from the surface of the incline, like so. We use this process to determine the direction of the maximum static friction force. The block is on the borderline of sliding up the incline. Friction opposes sliding. To prevent the block from sliding up the incline, the maximum static friction force will point parallel to and down the incline, like so. You should pause the video and memorize this process for determining the direction of the maximum static friction force. Now we have to determine the direction of the applied pushing force that someone is exerting on the block. Well, the problem tells us that that force is being exerted parallel to the surface of the incline. And it appears that the purpose of that force, so to speak, is to make the block start moving up the incline. So we know that this applied force should point parallel to and up the incline. Read and reread the problem carefully to make sure that you're getting all the necessary information. Now let's work on the force table. We are not given a value for the magnitudes of any of the forces. We do have special formulas, which we can use to calculate or represent the magnitude of the weight force and the magnitude of the maximum static friction force. Pause the video and make a note of what each of these symbols stands for. This symbol, written without an arrow on top of the letter F, stands for the magnitude of the maximum static friction force. The symbol mu sub s stands for the coefficient of static friction. And the symbol n, written without an arrow on top, stands for the magnitude of the normal force. This special formula only applies when we're assuming that static friction is at its maximum. If we were not assuming that static friction was at its maximum, then there would be no special formula for representing the static friction. Now, for an introductory course, most static friction problems will involve maximum static friction. So for most static friction problems, we will indeed use this formula. But you might occasionally see a static friction problem in which you're not assuming that static friction is at its maximum. And for that type of problem, There is no special formula for representing the magnitude of the static friction. Now, for this problem, we are assuming that we're at the borderline of sliding, which means that we are assuming that the static friction is maxed out. So for this problem, it is appropriate to apply this special formula for the magnitude of the maximum static friction. The reason that the block is on the verge of sliding is because at this borderline value, the static friction, which prevents the block from sliding, is maxed out. For mu sub s, we substitute the coefficient of static friction, 0.25. Be careful. Notice that for part A, we should not substitute 0.1. So here's how we can use this special formula to represent the magnitude of the overall maximum static friction force in the first row of our force table. There's no special formula for the magnitude of the normal force, so we represent that magnitude with a symbol. And there's no special formula for the magnitude of this applied pushing force. So we will simply represent the unknown magnitude of this applied pushing force with this symbol, capital F sub applied, written without an arrow on top, to show that this symbol stands for a magnitude. When there's no given value for a force and there's no special formula for a force, you simply represent the unknown magnitude of that force by a symbol in the first row of your force table. Before we break the forces into components, we must choose our axes. It's usually best to choose an axis that points in the object's direction of motion. In part A, we're assuming that the block is not moving, but the block is on the borderline of moving up the incline. And furthermore, looking ahead to part B, in part B, it turns out that the block really will be moving up the incline. So I'll choose a positive x-axis that points parallel to and up the incline. I'll choose a y-axis that points perpendicular to the incline. We can use this rule to break the normal force, applied force, and maximum static friction force into components. For example, our applied force points in the positive x direction. So the x component of the applied force is positive, and it has the same magnitude as the overall force, and the y component is 0. As usual, I put a plus sign in front of a positive component. The weight force is neither parallel nor anti-parallel to either axis, so rather than using this rule, we'll use SOHCAHTOA to break the weight force into components. If you found it easy to break the weight force into components, you can skip this part of the discussion using the table of contents. To represent the components, we draw a right triangle whose legs are parallel to our axes. On this problem, our x-axis is parallel to the incline, and our y-axis is perpendicular to the incline. So we draw a right triangle with one leg parallel to the incline, and one leg perpendicular to the incline. We use this rule to find the directions of the components. The head of a component should overlap with the head of the overall vector, and the tail of a component should overlap with the tail of the overall vector. Here, where we have the head of the overall vector, that should overlap with the head of this component. And here, where we have the tail of the overall vector, that should overlap with the tail of this component, which means that this is the head for this component. Now, we can determine the signs for the components. W sub x points down the incline, which is our negative x direction. So W sub x is negative. W sub y points into the incline, which is our negative y direction. So W sub y is also negative. This is the first problem in this video series for which both W sub x and W sub y are negative. It's crucial to get both of those negative signs correct. We can use geometry to determine that this angle alpha is 70 degrees, and use more geometry to determine that this angle beta is 20 degrees. We use absolute value symbols in the SOHCAHTOA equations because the SOHCAHTOA equations can only tell us the magnitudes of the components. It's our job to add plus or minus signs to the components in a separate step. We already decided that w sub x and w sub y are both pointing in our negative directions. So for this problem, w sub x and w sub y are both negative. Now we take our results for the components and enter them in our force table. These negative signs are crucial, so put a plus sign in front of your positive components so that you will notice when you need a negative sign in front of negative components. Now we're ready to work with the Newton's second law equations. Remember that for part A, we're assuming that the block does not slide, which means that for part A, the block is completely motionless. Since the block is motionless in both components, for part A, both components of the acceleration will be 0. So, for part A, we can substitute 0 for both a sub y and for a sub x in our Newton's second law equations. At this point, the Newton's second law x equation still has two unknowns, so we're not ready to work on that equation yet. The Newton's second law y equation has only one unknown, so we begin by solving the Newton's second law y equation for n, and we find that n equals 36.8 newtons. Then we take this result for n and substitute it into the Newton's second law x equation. Now the Newton's second law x equation has only one unknown, and we can solve this equation for F sub applied. And the result is that F sub applied equals 22.6 newtons. Now we can answer the question. The question was asking about the minimum force, but we're interpreting that to mean the magnitude of the force, since the direction of the force was already given in the problem, and we've discovered that the magnitude of that applied force is 22.6 newtons, which I'll round to 23 newtons. In our solution, we assumed that at the borderline force, the block would not slide. But now that it's time to write down our answer to the question, I'll go back to the wording that was used in part A, and now I'll interpret this number as the minimum force necessary to make the block start moving up the incline. Check that your results make sense. It makes sense that our result for n is positive because this symbol stands for a magnitude, and magnitudes can't be negative. It makes sense that our result for the magnitude of the normal force equals the magnitude of the y component of the weight, 36.8 newtons. The y component of the weight is trying to begin to drag the block into the surface of the inclined plane. To prevent that from happening, the normal force has to cancel the y component of the weight. This result came out to be positive, and that makes sense because the symbol F sub applied written without an arrow on top stands for a magnitude, and magnitudes can't be negative. Does this result for the size of the applied force make sense? 22.6 newtons. While the applied force is pushing up the incline, the applied force is trying to make the block begin sliding up the incline. But we know that in our solution for part A, we assumed that the block will not begin to slide. So this applied force is going to have to be canceled by W sub x together with the maximum static friction, which are both pointing down the incline. Well, earlier in our solution, we found the magnitude of W sub x, 13.4 newtons, and notice that in our algebra for the Newton's second law x equation, we determined that the magnitude of the maximum static friction force is 9.2 newtons. Well, 22.6 newtons equals 13.4 newtons plus 9.2 newtons. So yes, this result does make good sense. This result is exactly the size that it needs to be in order for the combination of W sub x and the maximum static friction to cancel the applied force. And we know that W sub x and the maximum static friction do have to cancel the applied force in order to prevent the block from beginning to slide up the incline. And in this version of the free body diagram, I tried to draw the length of the arrow for the applied force equal to the sum of the lengths of the arrows for W sub x and the maximum static friction. Now let's discuss part B of the problem. Here's a summary of the solution for part B. As we work on part B, we must carefully consider which parts of our solution to part A we can reuse for part B, and which parts of our solution to part A no longer apply to part B. Part B is asking for the acceleration of the block once it starts moving up the incline if this force is continually applied. Acceleration is a vector, so I will interpret this question as asking us for both the magnitude and the direction of the acceleration. Now let's make a plan for how we're going to answer the question for part B. Part B says this force is continually applied. Who do they mean by this force? Well, they mean the borderline force, which we just got finished determining in part A. In part A, we determined that the borderline applied force has a magnitude of 22.6 newtons. So I'll record here that the borderline applied force has a magnitude of 22.6 newtons. Part B says that that borderline force is continually applied in part B. So to solve part B, we're going to assume that the applied force equals 22.6 newtons, the borderline value. Now we know that at the borderline value, you can assume either that the block will slide or that the block will not slide, whichever is convenient for solving that part of the problem. So what's the convenient assumption to make for part B? Well, the question is asking us for the acceleration of the block once the block starts moving. It's impossible to figure out the acceleration of the block once it starts moving unless we assume that the block is moving. After all, if the block were not moving, then its acceleration would be zero. So for part B, we have to assume that the block does slide. We will assume that at the borderline applied force, the block does slide. And for this problem, that assumption will mean that at the borderline applied force, the block will be moving. So notice that for this problem, we're making two different assumptions about what happens at the borderline applied force for part A and for part B. It might seem strange that we can make those two opposite assumptions for different parts of the same problem, but it turns out that that is a valid problem-solving technique when you're thinking about the borderline value. This handout summarizes different types of problems involving friction. We've seen that part A of this problem involved this type, a maximum or minimum problem involving whether the object will slide. And now we can see that part B of this problem is this type of problem. Part B is a problem involving an object that we know is sliding. Well, that's good news because this is the simple type of friction problem that we already learned how to solve in the previous videos. So we've already learned this simple method. The simple method for this type of problem is to use the Newton's second law framework to apply kinetic friction because the object is sliding, and to use the special formula for the magnitude of kinetic friction in our force table. For part B, we've decided to assume that the block does slide up the incline. So for part B, the block will be moving up the incline, so we can draw the velocity vector pointing parallel to and up the incline to indicate the block's direction of motion for part B. Now we work on the free body diagram for part B. Now here is the free body diagram that we used for part A. Which parts of this free body diagram from part A can we reuse for part B, and which parts do we need to change for part B? Well, for part B, we're assuming that the block is sliding. So for part B, we should no longer be applying static friction. For part B, we have to begin applying kinetic friction. Here's the new version of the free body diagram that applies for part B. In part B, we're assuming that the block is sliding up the incline. So to oppose that, the direction of the kinetic friction will be parallel to and down the incline. There's no reason to make any changes to any of the other forces in our free body diagram. Now we work on the force table for part B. Now here is the force table that we came up with for part A. Which parts of this force table from part A can we reuse for part B? And which portions of the force table do we need to change for part B? Well, obviously, we need to change this part of the force table from part A. In part B of the problem, we assume that the block is sliding, so we're applying kinetic friction, not static friction. So for part B, we're going to use the special formula for determining the magnitude of kinetic friction. In this special formula, we have to substitute mu sub k, not mu sub s. So for part B, we no longer use this number 0.25. Instead, for part B, we have to use this number 0.1 to represent the coefficient of kinetic friction. Now here's another part of the force table from part A that we can update for part B. When we were working on part A, we didn't know what the magnitude of the applied force would be. That's what part A was asking us for. So we just represented the unknown magnitude with a symbol. But for part B, that force will be continually applied. That means that we can take the force that we determined from part A and use that number for part B. So for part B, we do know what the magnitude of the applied force will be. For part B, the magnitude of the applied force will be 22.6 newtons. That's the number that we determined in our work for part A. Now, what about the normal force? When we were working on part A, we eventually determined a value for the magnitude of the normal force. Should we reuse that value? Should we assume that the magnitude of the normal force in part B will be the same as in part A? Well, the safest approach is not to make that assumption. So for part B, I'm just going to represent the magnitude of the normal force with a symbol, and we will let the Newton's second law equations for part B determine for us whether the value of the normal force magnitude is the same for part B as it was for part A. Now we work on the Newton's second law equations for part B. Now for part B, the object will still be motionless in the y component. So we can still substitute 0 for a sub y for part B. For part B, we are assuming that the block does slide and move up the incline. So for part B, there's no reason to substitute 0 for a sub x. In fact, a sub x is what we're going to have to figure out in order to be able to answer the question. We begin by solving the Newton's second law y equation for n. Now notice that it did turn out that the magnitude of the normal force happens to be the same for part B as for part A. The magnitude of the normal force for part B is 36.8 newtons, and that happens to be the same magnitude of the normal force that we determined for part A. But we didn't assume that the normal force would be the same for part B as for part A. You may see other problems in which the magnitude of the normal force is different in part B than in part A. Then we can take our value for the magnitude of the normal force, substitute it into the Newton's second law x equation, and then solve that equation for a sub x. Now we can answer the question. I'm interpreting this question to be asking us about the magnitude and direction of the block's acceleration. A sub y is 0, so the magnitude and direction of the overall acceleration will be the same as the magnitude and direction of a sub x. A sub x is positive. Our positive x direction is parallel to and up the incline. So we can say that the direction of the overall acceleration is parallel to and up the incline. And I drew that acceleration vector here. And the magnitude of the acceleration, I'll round off to 1.4 meters per second squared. Now let's ask if our results make sense. Does it make sense that our result for the magnitude of the normal force turned out to be the same for part B as in part A? Well, in order to prevent the block from being dragged into the surface of the incline, the normal force has to cancel W sub y. W sub y is the same in part B as in part A. So yes, it does make sense that the magnitude of the normal force turned out to be the same in part B as in part A. Does our result for a sub x make sense? Does it make sense that a sub x is positive? The positive x direction is up the incline. So this result means that the acceleration points parallel to and up the incline. Does that make sense? Well, for part B, the block is beginning at rest and then starting to move up the incline. In order for the block to begin from rest and then begin moving up the incline, the acceleration must point up the incline. So yes, It does make sense that the acceleration points up the incline because that's the only way that the block could start moving up the incline. Now let's do a recap of our work on this problem. We saw that parts A and part B of this problem could be thought of as two different types of problems involving friction. Part A was a minimum problem involving whether the object will slide. For minimum or maximum problems of that type, we use the Newton's second law framework. We assume that the object is on the borderline of sliding. And for those types of problems, we assume that at the borderline value, the object does not slide. So that we apply static friction. We assume that static friction is at its maximum. We apply the special formula for the magnitude of the maximum static friction in the first row of our force table. Here's that special formula. And to determine a sub x and a sub y in the Newton's second law equations, we assume that the object does not slide. For part A of this problem, because we assumed that the block does not slide, we were able to substitute 0 for both a sub x and a sub y in our Newton's second law equations. On the other hand, for part B, we assumed that the object would be sliding at the borderline value, so we applied this simple method, which we've applied for the friction problems in the previous videos. We used the Newton's second law framework, we applied kinetic friction, and we used the special formula for kinetic friction. In part A, the object is on the verge of sliding parallel to and up the incline. So the maximum static friction force points parallel to and down the incline to prevent the object from sliding up the incline. Another feature of this problem is that it involves a force from somebody who is pushing on the block. We called that an applied force. In the first row of our force table, we represented the unknown magnitude of the applied force with a symbol, and then we used that symbol to help us represent the components. We saw that the key for part B was to carefully consider which parts of our solution to part A could be reused for part B, and which parts from part A no longer applied to part B. Part B told us that this force, which means the force we just determined in part A, is continually applied. So for part B, we used the value for the borderline applied force that we determined in part A. Here's a comparison of the assumptions that we made in our solution for part A and in our solution for part B. For part A, we assumed that the block does not slide at the borderline applied force. For part B, we assumed that the block does slide at the borderline applied force. Here's a side-by-side comparison of some of the key steps in our solutions for part A and for part B. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.